Welcome to Max and Lizzie's Video Lab Report. This is week 2 of Circuits Lab, and we are focusing on music and sound today.
The first part of this experiment will be to identify the frequencies of the 4 pitches from the opening phrase of Beethoven's Fifth Symphony.
To do this, we connected a laptop to an oscilloscope and a speaker. We played the sound clip and used the run-stop function on the oscilloscope to capture an image of the wave function for each note. From the readout on the scope monitor, we were able to calculate a frequency for each of the 4 pitches, which can be seen in this table. We converted the frequencies to pitches using the given conversion chart, and then compared them to the actual pitches that Beethoven used in his symphony. As you can see, the notes we calculated are similar to the notes Beethoven composed, but some of the notes are in different octaves.
There are various reasons for this. The first is that we measured the frequency of instruments that naturally play in higher or lower registers, or we measured one of the harmonic overtones of the same note.
For our experiment, we chose to explore this Jewish instrument, the shofar. A shofar is a ram's horn that is blown on various religious occasions. As Max will shortly demonstrate, the shofar can be played at a few different pitches, and our objective in this experiment is to determine the frequencies of those pitches. Max will now demonstrate the range of pitches that we will analyze in our experiment. Just kidding. The lowest pitch actually sounds like this.
For this experiment, our materials are this shofar, my lungs, this microphone, and our friend the LaCroix oscilloscope. To take data, I played the shofar. Do you want me to play it?
Yes.
Okay. Like that. While Lizzie used the run stop button on the oscilloscope function to take a screenshot resulting in this wave. We were then able to analyze the data by adjusting the wave. Oops. And then we also used the math function to create an FFT, which is a Fourier transform, which shows the different the amplitudes of the different sine function components of the wave. So you can see that the wave is not actually made up of one sine function, but several different sine functions at decreasing amplitudes.
This picture of the scope readout corresponds to the highest pitch Max played on the shofar. This wave has a period of 1.4 milliseconds, which gives us a frequency of 714 Hz.
The next picture is of the scope readout for the middle pitch. The period of this wave is 2 milliseconds, which gives us a frequency of 500 Hz.
The final picture of the scope readout corresponds to the lowest pitch. The period of this wave, measured from the tips of the highest of the peaks, is 3 milliseconds. The lowest pitch has a frequency of 333 Hz. The table shown is a compilation of all of our data for this experiment. On the left side, we show the recorded period and derived frequency for all of the 3 pitches that we recorded, as well as the equivalent note based on the conversion chart that we used in the Beethoven experiment.
On the right side of this table is our attempt to find expected values for the first 3 fundamental frequencies of the shofar. So what we did is we found the wavelength of the first 3 fundamental standing waves using an equation for a standing wave, and the measured length of the shofar, which we estimated to be 0.4 meters. And then we used that and the speed of sound in air to find the frequencies of these first 3 standing waves. As you can see, they correspond slightly to what we expect, in that the first fundamental frequency is within 100 hertz, the second is within about 200, and the third is within about 300 hertz. So they're on the right order of magnitude. However, they're not very close, and that makes sense because we used an equation for a cylinder as opposed to the shofar, which has a very strange, twisty shape.
conclusion, we were able to find the first 3 fundamental frequencies of the shofar using period measurements from an oscilloscope. Even though we weren't able to match the theoretical frequencies exactly, we can justify these discrepancies. This is clearly not a straight cylinder. It was very interesting to learn about an instrument that Max and I have heard for so long, and it was also fun to apply theory and methods from our circuits class to music.
Thanks for watching. Tune in next week for Lab 3.